Imagine for a moment that everything you've ever been taught about reality is fundamentally incomplete. Not wrong exactly, but like being shown only the shadow of an object and asked to describe its true form. The three-dimensional world we perceive, the solid chair beneath you, the device you're reading this on, even your own body, might be an elaborate projection of information from a reality with dimensions and properties our brains aren't equipped to process directly. In 1974, physicist John Wheeler posed a deceptively simple question that continues to haunt the halls of theoretical physics. How come existence? Three small words that strike at the very foundation of reality. Not just why does the universe exist, but how does anything exist at all? What is reality made of at its most fundamental level? The answers have proven far stranger than anything taught in standard textbooks, and they challenge not just what we know, but how we know it. The story of our modern understanding of reality begins, perhaps surprisingly, with a mathematical puzzle. In the early 20th century, physicists were struggling with a problem. When they tried to calculate what happens when light interacts with matter, their equations kept giving infinite answers. Clearly nonsensical, these infinities suggested something was fundamentally wrong with how we understood the physical world. Enter Richard Feynman, a brash young American physicist with an unorthodox approach to problem solving. In 1948, while working at Cornell University, Feynman developed a technique called renormalization that effectively swept these infinities under the mathematical rug. The technique worked brilliantly, allowing precise predictions about the behavior of particles. But Feynman himself remained deeply troubled by it, calling it hocus pocus and a dippy process. The shell game that we play is technically called renormalization, Feynman later wrote. But no matter how clever the word, it is still what I would call a dippy process. Having to resort to such hocus pocus has prevented us from proving that the theory of quantum electrodynamics is mathematically self-consistent. What troubled Feynman was that renormalization seemed like a mathematical trick rather than a true understanding. It was as if nature was telling us something profound about reality, and we were covering our ears. Around the same time, another physicist was grappling with similar questions from a completely different angle. In Princeton, New Jersey, John Archibald Wheeler, a visionary who had worked on the Manhattan Project and collaborated with Einstein, began to suspect that the fundamental nature of reality might be entirely different from what we had imagined. Wheeler, known for coining evocative phrases to capture complex ideas, proposed that it from bit, suggesting that physical objects, it, emerge from information, bit. Reality at its most fundamental level, Wheeler proposed, might not be made of tiny physical objects like atoms or particles, but of information itself. All things physical are information theoretic in origin, Wheeler wrote in 1990. This is a participatory universe. Observer participancy gives rise to information, and information gives rise to physics. This radical proposal that information might be more fundamental than matter seemed almost mystical when first proposed. But as the decades passed, evidence began mounting that Wheeler might have been onto something profound. The question now became, if reality is built from information rather than matter, what does that actually mean for how the universe works? And how could we possibly test such an abstract idea? The answer would come from an unexpected direction. Black holes. On March 26, 1974, Stephen Hawking published a paper that would change theoretical physics forever. In it, he made the stunning prediction that black holes, objects so massive that not even light can escape their gravitational pull, aren't completely black. Instead, they emit a faint radiation, now called Hawking radiation. This created an immediate paradox. According to quantum mechanics, this radiation is completely random, containing no information about what fell into the black hole. But this would violate a fundamental principle of physics. Information cannot be destroyed. If you burn a book, the information it contained isn't gone. It's converted into the precise pattern of smoke, ash, and heat. Complex, yes, but theoretically recoverable. Yet black holes seem different. They appeared to be cosmic information shredders, permanently erasing whatever fell into them once they eventually evaporate through Hawking radiation. This contradiction between quantum mechanics and general relativity became known as the black hole information paradox, and it remains one of the most profound problems in physics. Not only does God play dice, Hawking famously quipped, modifying Einstein's famous objection to quantum randomness, but sometimes he throws them where they cannot be seen. But the plot thickens. In 1993, Dutch physicist Gerard T. Hooft proposed a mind-bending solution called the holographic principle. Drawing on string theory calculations by Leonard Susskind, T. Hooft suggested that all the information about objects that fall into a black hole might actually be preserved, not inside the black hole but encoded on its two-dimensional surface or event horizon. This seemingly technical solution to a specific problem rapidly expanded into something far more profound. If information about three-dimensional objects could be completely encoded on a two-dimensional surface, could our entire three-dimensional reality be a projection of information stored on a distant two-dimensional boundary? The mathematics suggested something extraordinary. Our three-dimensional reality might be equivalent to a two-dimensional reality without gravity. Different descriptions of the same underlying reality, like describing water as either a liquid or as a collection of H2O molecules. Juan Meldacena, a soft-spoken Argentine physicist working at the Institute for Advanced Study in Princeton, where Einstein once worked, formalized this idea in 1997 with what became known as the ADS/CFT correspondence, arguably the most important theoretical physics discovery in the past 25 years. The theory suggests that the universe is a kind of hologram, explained Meldacena. The physics occurring within a volume of space can be described by a theory residing on the boundary of that space, much like a hologram, which presents a three-dimensional image when light bounces off a two-dimensional surface. But what does it mean to say reality is a hologram? Unlike the holograms in science fiction, the universe isn't a projection created by some advanced technology. Rather, the holographic principle suggests that the most fundamental description of reality might require one fewer dimension than we perceive. Our three-dimensional experience emerges from information encoded in a two-dimensional form. This theoretical discovery soon found unexpected experimental support. In 2013, physicist Yoshifumi Hayakatake and colleagues at Ibaraki University in Japan provided computational evidence for the holographic principle. They calculated the internal energy of a black hole using standard physics, then calculated the energy of the corresponding lower-dimensional system described by quantum theory without gravity. The results matched perfectly. This is an exciting suggestion, said theoretical physicist Sabine Hassenfelder from the Frankfurt Institute for Advanced Studies. But we still don't know whether our universe actually satisfies the conditions necessary for this holographic description to apply. The implications are staggering. If true, the holographic principle means that the reality we experience, three-dimensional space with its galaxies, planets, buildings, and people, emerges from a more fundamental reality that might operate according to entirely different principles, much as the moving images on your computer screen emerge from the underlying binary code. But the mysteries of reality's true nature don't end with dimensionality. Quantum mechanics, the theory governing the behavior of matter at the smallest scales, reveals an even deeper level of strangeness. Consider the famous double-slit experiment, first conducted with light by Thomas Young in 1801, but later replicated with electrons, atoms, and even small molecules. When individual particles are sent through two parallel slits, they don't simply go through one slit or the other as common sense would suggest. Instead, they create an interference pattern as if each particle somehow goes through both slits simultaneously, behaving like a wave of possibilities rather than a definite object. Even stranger, if you place detectors at the slits to observe which one each particle goes through, the interference pattern disappears. The mere act of observation seems to collapse the wave-like behavior into particle-like behavior. If you think you understand quantum mechanics, you don't understand quantum mechanics, Nobel laureate Richard Feynman famously remarked. The standard interpretation of these results, the Copenhagen interpretation, suggests that particles exist in a superposition of multiple states until they're observed or measured. The act of measurement collapses this superposition into a single definite state. But what constitutes a measurement? Does it require a conscious observer? For decades, physicists have debated what this strange quantum behavior tells us about reality's true nature. In 1957, Hugh Everett III proposed a radical alternative called the many-worlds interpretation. Perhaps reality doesn't collapse at all. Instead, every possible outcome actually occurs, in separate, branching realities that can't interact with each other. According to this view, the universe constantly splits into countless parallel versions, each one representing a different outcome of quantum events. The idea of 10 to the power of 500 slightly different copies of you, reading this sentence in slightly different parallel universes, is not a metaphor, it's reality, writes Max Tegmark, a cosmologist at MIT. Other interpretations abound. Perhaps information rather than matter is fundamental, as John Wheeler suggested. Perhaps consciousness plays a key role, as proposed by Eugene Wigner and later developed by John von Neumann. Perhaps reality is fundamentally non-local, with instantaneous connections between entangled particles regardless of distance, as implied by Bell's theorem and confirmed by experiments. Each interpretation preserves the mathematics of quantum mechanics while telling a different story about what reality is actually doing behind the scenes. And crucially, each makes identical predictions about the outcomes of experiments, making them scientifically indistinguishable for now. Nature, as physicist Pascual Jordan put it, is conformable to herself, suggesting that reality must possess an underlying coherence, even if our current theories seem mutually incompatible. This brings us to perhaps the most profound mystery of all, time itself. According to Einstein's relativity, time is not absolute but relative, flowing at different rates depending on gravity and velocity. Two synchronized clocks will disagree after one travels near the speed of light or spends time in a strong gravitational field. This has been confirmed countless times by experiments with atomic clocks on airplanes and satellites. But quantum mechanics suggests something even more radical. At the most fundamental level, the laws of physics work the same whether time runs forward or backward. There's no inherent arrow of time in the basic equations. Yet our macroscopic experience features a clear direction. Eggs break but don't unbreak. Coffee cools but doesn't spontaneously heat up. People age rather than growing younger. This one-way flow of time is explained by the second law of thermodynamics. Entropy, disorder, tends to increase over time. But why did the universe begin in a low-entropy state to begin with? And what does it mean that time itself might be emergent rather than fundamental? Time is nature's way of keeping everything from happening at once, quipped physicist John Wheeler. But the joke hints at a profound truth. Time might not be what we think it is. Some theoretical physicists, including Julian Barbour, have proposed that time is entirely illusory, a psychological construct rather than a fundamental dimension. In this view, reality consists of a vast collection of nows, complete moments that exist simultaneously. Our sense of flow is just how our consciousness moves from one now to another. If you try to get your hands on time, it's always slipping through your fingers, says Barbour. People are sure time is there, but they can't get hold of it. My feeling is that they can't get hold of it because it isn't there at all. Others, like Carlo Rovelli, developer of loop quantum gravity, suggest that time emerges from quantum entanglement between systems. When particles become entangled, they can only be described in relation to each other, not as independent entities. Perhaps time is similar, not a fundamental property but a relationship between events. Time is a derived concept, not a primary one, argues Rovelli. Our sense that time flows from past to future is an approximation valid for our macroscopic scale. These ideas are more than philosophical musings. They have profound implications for our understanding of reality's true structure and may hold the key to resolving the apparent contradictions between quantum mechanics and general relativity, our two most successful but mutually incompatible theories. The plot thickens further when we consider what might be the most counterintuitive discovery of all, the possibility that reality itself might be made of computation. On a warm June day in 1956, during a symposium on information theory at Dartmouth College, the mathematician and computer scientist John McCarthy coined a term that would eventually transform our understanding of reality itself: artificial intelligence. That summer's workshops marked the official birth of AI as a field, but they also planted the seeds for something even more profound: the computational theory of everything. The central insight was deceptively simple. Information processing isn't just something humans do with computers. It might be what the universe itself is doing at every moment. This idea took formal shape in the work of physicist Edward Fredkin, who proposed in the 1960s that the universe might fundamentally be a cellular automaton, a discrete computational process similar to John Conway's later Game of Life. where complex patterns emerge from simple rules applied iteratively. I don't believe that the laws of physics are built on top of mathematics, Fredkin explained. I believe they're built on top of computation. At first dismissed as speculative, this computational view of reality gained surprising support from black hole thermodynamics. In 1972, Jacob Bekenstein calculated that a black hole's entropy, roughly the amount of information it contains, is proportional to the area of its event horizon, not its volume as one might expect. This strange area scaling property matched exactly what you'd expect if reality worked like a holographic projection, with information stored on a lower dimensional boundary. But it also resembled how information is processed in certain computational systems. The connection grew stronger in the 1990s when Gerard T. Hooft and Leonard Susskind formally proposed the holographic principle. If information in any region of space is limited by the region's boundary area rather than its volume, it suggests a fundamental limit to information density that aligns perfectly with computational models. Meanwhile, quantum mechanics already described reality in terms strikingly similar to information processing. Quantum superposition resembles parallel processing, where multiple possibilities are evaluated simultaneously. Quantum entanglement creates correlations that can be understood as information shared between systems. In 2019, Google's quantum computer performed a calculation in 200 seconds that would take the world's most powerful supercomputer 10,000 years, demonstrating the immense computational power inherent in quantum systems. But perhaps the most compelling evidence came from an unexpected direction: quantum gravity. For decades, physicists have struggled to reconcile quantum mechanics, governing the very small, with general relativity, governing the very large. The theories work beautifully in their respective domains but break down when applied together, such as inside black holes or during the Big Bang. In 1998, theoretical physicist Juan Meldacena published what has been called the most important theoretical physics result of the past 25 years. A precise mathematical relationship between a gravitational theory in a space with 5 dimensions and a quantum theory without gravity on that space's 4-dimensional boundary. What made this correspondence revolutionary wasn't just that it connected quantum mechanics with gravity, but how it did so through a relationship mathematically identical to certain quantum error-correcting codes used in quantum computing. It's as if the fabric of space-time emerges from quantum entanglement, explained Mark van Ramsdonk from the University of British Columbia. This connection was formalized in 2015 by Ahmed Elmhiri, Shi Dong, and Daniel Harlow, who demonstrated that the holographic correspondence works exactly like a quantum error-correcting code, a technique developed for quantum computing that protects quantum information from decoherence. Space-time itself seems to be woven from quantum bits, said Elmhiri. The interior of space-time is encoded redundantly in these boundary degrees of freedom. By 2022, physicists like Ning Bao were writing papers with titles like Quantum Error Correction and Large N that made the connection explicit. Gravity is error correction. Meanwhile, computer scientists were approaching the same conclusion from another direction. Scott Aronson, a theoretical computer scientist at the University of Texas, Austin, pointed out that quantum computational complexity, how many quantum operations are needed to perform a task, matches precisely with the growth of wormholes in certain gravitational theories. We're discovering that concepts developed for practical quantum computing are deeply related to how space-time works, Aronson explained. This convergence of quantum information, computation, and gravity suggests something profound. The reality we experience might be the output of a vast quantum computation. Not a simulation created by some advanced civilization, but reality itself functioning as a computational process. This view aligns with physicist John Wheeler's famous dictum, "It from bit," the proposal that physical reality emerges from information. Wheeler was among the first to recognize that information might be more fundamental than matter or energy. What we call reality, Wheeler wrote, arises in the last analysis from the posing of yes-no questions. All things physical are information theoretic in origin. If reality is indeed computational at its core, it would explain several mysterious features of our universe. First, the existence of a minimum length scale in physics, the Planck length of about 10 to the power of -35 meters, below which our concepts of space break down. This resembles the pixels or minimal units in a computational system. Second, the universal speed limit, the speed of light, which could represent the maximum rate at which information can propagate through the computational substrate. Third, the pervasive role of mathematics in describing physical laws. If reality is computational, mathematics isn't just a human invention that happens to describe nature. It's the actual language reality is written in. Fourth, quantum indeterminacy and randomness, which resemble the probabilistic algorithms used in quantum computing. And perhaps most profoundly, this view might explain consciousness itself. If reality processes information at its most fundamental level, then consciousness, also an information processing phenomenon, might be connected to reality's underlying nature in ways we're only beginning to understand. In 2014, neuroscientist and psychiatrist Giulio Tononi proposed integrated information theory, suggesting that consciousness arises from complex, integrated information processing. The theory quantifies consciousness through a measure called phi, which represents how much a system's information exceeds the sum of its parts. If reality itself is computational, consciousness might not be a strange emergence from otherwise dead matter, but a natural extension of reality's fundamental information processing nature, simply operating at a different level of complexity and integration. Consciousness doesn't happen in here, says philosopher Alva No, pointing to his head. It's something we do, a kind of dance with the world. This computational view of reality doesn't reduce the mystery of existence. It deepens it. The question becomes not just how the universe computes, but why this particular computation. What selected these specific physical laws from all possible computational rules? And if reality is computation, what is the hardware it runs on? Or is there no hardware, just information all the way down? These questions lead to what might be the most profound turning point in our understanding of reality. The growing recognition that what we experience as physical reality might be just one layer of a much deeper structure, a structure whose true nature could be entirely different from anything we've imagined. If reality is fundamentally computational and holographic, with our three-dimensional world emerging from information encoded on a lower-dimensional boundary, what does this mean for our understanding of existence? The implications extend far beyond abstract physics, touching every aspect of how we perceive ourselves and our place in the universe. First, it transforms our understanding of space. What we experience as the continuous three-dimensional space around us, the room you're sitting in, the distance to distant stars, might be an emergent phenomenon, like the seemingly continuous images on a digital screen that are actually made of discrete pixels. Space itself wouldn't be fundamental but would emerge from relationships between more basic quantum bits of information. Space is built from entanglement, explains physicist Mark van Ramsdonk. The connectivity of space, which points are near which other points, is encoded in the pattern of entanglement between the fundamental quantum variables. This explains why entangled particles can show correlated properties instantaneously across any distance. They're not communicating through space. Rather, space itself emerges from their entanglement. Similarly, our understanding of time undergoes a radical shift. In a computational universe, time might not flow continuously but advance in discrete steps, like the clock cycles of a computer. What we experience as the smooth passage of time might be more like the rapid succession of frames in a movie, creating the illusion of continuous motion. Time is not a primitive notion, argues physicist Fotini Marcopola. In quantum gravity, time emerges from more fundamental quantum processes. Even more profound is the implication for causality, our deep-seated belief that events proceed from cause to effect in a linear sequence. In a holographic, computational reality, causality might be an emergent feature rather than a fundamental law. Different slices of reality might represent different computational states, with our perception of cause and effect simply reflecting how we navigate through them. This possibility aligns with certain interpretations of quantum mechanics, like the transactional interpretation proposed by John Cramer, where quantum events involve handshakes between waves propagating both forward and backward in time. For matter and energy, the stuff we normally think reality is made of, the implications are equally profound. If information is fundamental, then matter and energy might be particular patterns or configurations of information rather than primary substances. Just as the text you're reading now exists as patterns of information that can be displayed on different physical media, perhaps physical particles are patterns that can be instantiated in different computational substrates. Matter is not what reality is made of, writes physicist Max Tegmark. Rather, matter is merely a convenient way of describing certain particularly stable and predictable information patterns. This view helps explain why mathematical equations describe physical reality so effectively. If reality is computational at heart, mathematics isn't just a human invention that happens to describe nature, it's the actual language reality operates in. The implications extend to biology as well. DNA, the information-carrying molecule at the heart of all known life, can be understood as a digital code, with its 4 nucleotide bases, A, T, G, C, functioning like a quaternary numeral system rather than the binary system used in conventional computing. Life is just bytes and bytes of digital information, explains synthetic biologist J. Craig Venter, who created the first cell with a synthetic genome. This informational view of life aligns perfectly with a computational view of reality itself. Perhaps most significantly, this new understanding of reality has profound implications for consciousness, the mysterious first-person experience of being aware. If information and computation are fundamental aspects of reality, then consciousness, also an information processing phenomenon, might not be a strange emergence from otherwise dead matter. Instead, it could be connected to reality's underlying nature in ways we're only beginning to understand. Some philosophers, like David Chalmers, suggest consciousness might be a fundamental aspect of reality alongside information, an idea called panpsychism. Others, like Giulio Tononi, propose that consciousness emerges specifically from integrated information processing that creates a unified experience. Consciousness is integrated information, explains Tononi. Not just any information, but information that is highly differentiated, rich in distinctions, and highly integrated, unified into a coherent whole. This integrated information theory provides a mathematical framework that potentially connects consciousness to the computational fabric of reality itself. It suggests conscious experience might be what information processing feels like from the inside. The computational view of reality also transforms our understanding of human knowledge. If reality functions like a vast quantum computation, our theories about it aren't simply descriptions of an external world. They're models running on the neural computation of our brains, which itself is part of the larger computation of reality. All models are wrong, but some are useful, statistician George Box famously observed. In a computational reality, this becomes profoundly true. Our scientific models are necessarily simplified algorithms that approximate aspects of a vastly more complex computation. This helps explain why quantum mechanics seems so counterintuitive. Our brains evolved to model the macroscopic world relevant to our survival, not the fundamental computational substrate of reality itself. It also suggests that mathematics, logic, and computation aren't just human inventions but discoveries about the fundamental nature of reality. When mathematicians prove theorems or computer scientists analyze algorithms, they're exploring the same computational structure that underlies physical reality. The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve, wrote physicist Eugene Wigner in 1960. The computational view suggests this miracle is no accident. Mathematics works because reality itself is mathematical at heart. Perhaps most provocatively, a computational view of reality changes how we think about the multiverse, the hypothesis that our universe is just one of many possible universes. In a computational framework, these parallel universes might represent different runs of the same fundamental algorithm with different initial conditions or parameters. The mathematical structure of reality is so enormous and rich that it must contain multiple universes, argues physicist Max Tegmark. Our physical universe is just one possible solution to the equations governing reality. This view suggests that the seemingly arbitrary physical constants of our universe, like the strength of gravity or the mass of elementary particles, might be analogous to variables in a computer program. Different universes would feature different values of these variables, creating entirely different physical realities. Some of these universes might collapse instantly, others might never form stars or atoms, and a tiny fraction, including our own, might have just the right settings to allow complex structures like galaxies, planets, and living beings to emerge. The multiverse isn't a theory, it's a prediction of theories we already have, explains cosmologist Sean Carroll. This computational multiverse isn't mystical speculation but a mathematical consequence of our best current theories. But perhaps the most profound implication is philosophical. If reality is fundamentally computational and information theoretic, it suggests a universe that's neither purely material, as traditional physicalism holds, nor dependent on consciousness, as idealism suggests, but informational at its core. This view, sometimes called informationalism, suggests that both matter and mind might be different aspects of the same underlying informational reality, like hardware and software in a computer system, or different layers in a complex computation. Information is physical, stated physicist Rolf Landauer, but perhaps the reverse is also true. The physical is informational. Matter, energy, space, and time might all be particular patterns or structures within a more fundamental informational reality. In this view, the universe isn't a collection of objects but a process, a vast, ongoing computation that generates what we experience as physical reality. And we ourselves are complex patterns within that computation, capable of modeling and understanding aspects of the larger process. This brings us full circle to John Wheeler's profound question, how come existence? In a computational universe, existence itself might be understood as information in a self-referential process, reality computing itself into being. As our journey through the hidden architecture of reality concludes, we find ourselves standing at a precipice of understanding unlike any in human history. The universe we inhabit is not the solid, continuous, three-dimensional realm we were taught in school, nor is it the clockwork mechanism of classical physics. It is something far stranger and more profound, a vast informational structure whose true nature transcends our everyday experience. The poet William Blake wrote of seeing a world in a grain of sand and a heaven in a wild flower. Today's physicists might speak instead of seeing the computational fabric of reality in every quantum interaction, the holographic principle encoded in every region of spacetime, and the patterns of information that constitute both the stars above and the awareness within us. This new understanding doesn't diminish the wonder of existence. It amplifies it. When we look at the night sky, we're not just seeing distant suns but glimpsing the output of a cosmic computation that generates space, time, and conscious experience itself. When we look into another person's eyes, we're witnessing another node in this vast informational network, processing reality from another unique perspective. The universe is not just stranger than we imagine but stranger than we can imagine. Yet paradoxically, this strangeness becomes comprehensible through the language of information and computation that we ourselves have developed. Perhaps the most profound insight is that we are not passive observers of an external reality but active participants in the informational processes that constitute reality itself. John Wheeler captured this participatory aspect of reality when he wrote, "The observer is as essential to the creation of the universe as the universe is to the creation of the observer." In this light, scientific exploration becomes not just the study of an external world but a form of self-reference, the universe examining itself through the localized consciousness that we call human awareness. Our theories, our experiments, our very thoughts are patterns in the same computational fabric that constitutes stars and galaxies. This perspective transforms how we understand consciousness as well. Rather than an inexplicable emergence from supposedly dead matter, consciousness might be what information integration feels like from the inside, a natural manifestation of reality's underlying computational nature, experienced at a particular scale and level of complexity. As physicist Max Planck observed in 1931, I regard consciousness as fundamental. I regard matter as derivative from consciousness. In a computational universe, both consciousness and matter might be different aspects of the same underlying informational reality. This doesn't mean reality is a simulation created by some external programmer, but rather that computation isn't just something humans invented, it's what the universe itself does, and perhaps always has done, generating what we experience as physical reality from deeper informational processes. The recognition that reality's true shape may be computational and holographic rather than simply physical represents perhaps the most profound scientific revolution since the quantum and relativistic transformations of the early 20th century. It suggests a universe that's both mathematically intelligible and endlessly creative, generating complexity and consciousness through fundamental informational processes. In this new understanding, we find not a cold, mechanical cosmos but one vibrant with possibility, a universe computing itself into existence, generating both the complexity we observe around us and the consciousness with which we observe it. This isn't just a new theory but a new relationship between ourselves and reality, one that recognizes our deep connection to the informational fabric of existence itself. The world taught in classrooms of solid objects moving through absolute space and time was never the whole story, just a useful approximation. Reality's true shape appears to be a vast computational process generating not just the physical world we perceive but the very consciousness with which we perceive it, binding observer and observed in an intricate dance of information and meaning. In the end, what they never teach you in school about the real shape of reality is that you are not simply in the universe. The universe is also in you, both observer and observed emerging from the same fundamental patterns of information that constitute reality itself.